In this video, I want to talk about the process of computing the factorial function recursively. So here I have my factorial function set up. So this is how it works. We saw it a couple of times. So you have your base case where you say if n is equal to 0, then 0 factorial is just defined as 1. And then you have your recursive call, which is return n times factorial of n minus 1, and that's because we know that mathematically n factorial is equal to n times n minus 1 times n minus 2 and so on down to 1, which is in turn equal to n times n minus 1 factorial. So okay, let's run it once just to make sure that it works. Here we have it. 6 factorial is 720. And what I want to do now is I want to trace it. So I'll put my breakpoint here on line 14 and I'll run it again. Alright, so here I'm making the call to factorial 6. Let's step in. So when the first call happens, there is nothing at all mysterious that's going on. You're just calling factorial with n equals 6. Let's go line by line. If n equals 0, return 1, but n is not 0, n is equal to 6. So now we get to the recursive call. Now, here, what you can think about it this way. You can say, okay, well, factorial is just a helper function. In order for me to compute factorial of n, I get to call my helper function, which also happens to be factorial, with the argument n minus 1. So I'll get this value, factorial of n minus 1, so factorial of 5, I'll multiply it by 6, and I'll return my result. So in order for us to compute factorial n minus 1, we got to call it. So let's make the call now, and let's step in again. So we're calling factorial n minus 1. Okay, here we are. So we called factorial with n equals 5. Here we are. So now we're computing factorial of 5. Now the important thing to remember and to understand is that the call to factorial 6, it still exists. So we can actually go back and see that here n is equal to 6. So what I did is I switched to a different call, like so, and here n is equal to 6. I can also switch back to line 14 from where I called factorial of 6 to begin with. Here, of course, n is not even defined anywhere. So, okay, let's go back to our call to factorial 5. So here, n is equal to 5, so not 0, so we go to the next line. And again, in order to return factorial of 5, we got to first compute factorial of 4, then multiply it by 5, and then we'll have our return value. Let's step in again. And what you see is that the call stack keeps growing. So right now the call stack has 4 frames in it, and it'll grow further. So now we see that n is equal to 4. Let's again step through all the lines. And now we step in again, so we call factorial of 3. So now in this call, n is equal to 3. Of course, in the previous call, n is equal to 4. Let's go to the top call now. And again, here again, we need to call factorial of 2. And here we need to call factorial of 1. And here something that's more straightforward is going to happen. So n is equal to 1, as you see. So we need to return 1 times factorial of 0. Now, factorial of 0 is it's easy to understand, because if you call factorial with n equals 0, then, well, n equals 0, so it just returns 1 straight away. There is no recursive call. So factorial 1 is going to return 1 because this is 1, and this, factorial 0, will return 1 in short order. So it's going to be 1 times 1 equals 1. So let's make sure that this is exactly what happens. So we call factorial n minus 1, so factorial 0. And here we are, n is equal to 0. And now we finally get to this if statement where the condition holds, so we got to return 1. So factorial 0 is about to return 1. If we look in the call stack, what we see is that over here, where n is equal to 1, this call to factorial 1 is waiting for factorial 0 to return. Once factorial 0 returns, it can compute 1 times factorial 0 and return the result. Let's pick another random frame here. So here n is equal to 4. That's also in memory, so we have multiple locals tables, which for the different calls to factorial, each of which contains a different value of n, so we remember all the values of n here. And here we are just waiting for factorial of n minus 1, so factorial of 3 to return. So that'll happen eventually. Right now, let's go back to the top of the stack, where we are wanting to return 1. So once we return 1, we are now here, n is equal to 1, and factorial 0 just returned 1, so we are about to return 1 times 1 to the call factorial 2, which is waiting for the result of factorial 1. And now n is equal to 2, and we're about to return n times factorial 1. We just got the result for factorial 1. And now we are back, so if you look here, you'll notice that the stack is getting shorter and shorter because we keep returning. So now we return from factorial 3, and now we're returning from factorial 4, now we're returning from factorial 5, and now we're about to return from factorial 6, and what we'll return is 6 times this newly computed value, factorial 5. So the return value. So if we just say continue, we'll get our 720. So let's look at it from the point of view of the call tree. So the first call was to factorial 6. Then inside factorial 6, we made the call to factorial 5. Inside factorial 5, we made the call to factorial 4. Inside factorial 4, we made the call to factorial 3, and then from there we called factorial 2, and from there we called factorial 1, and from there we called factorial 0. Now, factorial 0 makes no calls, because when n is equal to 0, we just return 1. So that means that factorial 0 just returns 1. What does factorial 1 return? Well, factorial 1 returns 1, because n is equal to 1, times whatever factorial 0 computes, which happens to be 1. What about factorial 2? Well, factorial 2 returns 2 times whatever factorial 1 computes, right? So if we were to expand this expression factorial 1, we'll get this guy. So let's just write it like that. This is what we get. Now what about factorial 3? Same thing, so it's 3 times this whole thing if we expand the expression factorial 2. So it's going to be like this. And now 4 again, it's going to be 4 times this whole thing, factorial 3. And 5 is going to be 5 times, you see the pattern here, this thing. And then 6 is going to, factorial 6 is going to be 6 times this whole thing. So this is basically what happens when you're trying to compute factorial of 6 using this recursive function. essentially you're expanding the computation. And when factorial 0 returns, well, then factorial 1 has this value, and it gets to compute it. And once factorial 1 returns, factorial 2 has this value, and now it can compute 2 factorial. And so on, down to 6 factorial. So we make the calls, so factorial 6 calls factorial 5, that one calls factorial 4, and so on. And when you're making the calls, you're still not doing any multiplications. So at the point when factorial 0 got called, we have all of those n's, 6, 5, 4, 3, 2, 1, 0, all stored in the different locals tables for the different calls to factorial. And now once we have all of those guys stored, then we go back and we do the computations. So once factorial 0 returns, we can compute factorial 1, and then factorial 1 returns, we can compute factorial 2, and so on, down to factorial 6. So we do some computation, subtracting 1 from n every time, going up the call tree, and then as we go down the call tree, we actually do the computation of n factorial.